Hi, I'm Darren and welcome to Level Up Double E Lab. My regular viewers will certainly recognize this guy, my home-built HF transmitter. Now, I did a 20-part series about a year ago on the design and construction of this guy, and there were a couple of improvements that I wanted to look at in the future. And we're going to get to one of them today, the microphone preamp. Let's get started. This is my home-built HF amateur radio transmitter. I showed its design and construction in a series of 20 episodes about a year ago. I built it to use a specific Kenwood microphone that unfortunately I no longer have. I sold it and the Kenwood rig that it went with a few months ago. So I need a replacement. But rather than replace it with an identical mic, this is a good opportunity for me to fix a shortcoming with the existing audio front-end circuit. Here's the block diagram: a mic preamp, a low-pass filter section, and then the balance modulator. The issue is there's no automatic gain control in this section. All that I have is a potentiometer here at the input to the balance modulator to adjust the audio level. And not having AGC meant that I constantly struggled getting full dynamic range from my spoken voice. If I set this pot too low, then my output power suffered. But if I set it too high, then I drove the RF stages into saturation and distortion. And if I moved toward and away from the mic while speaking, I could create both issues. So I really need some form of AGC in here. I lifted almost all of the audio and IF circuit design from Chapter 6 of the Experimental Methods in RF Design book. And actually, EMRFD does show an improved IF design with diode clipping. That's a crude form of gain control. But I have another idea to try here, one that uses a more modern approach. What if I had active gain control right here in the first stage, the microphone amplifier? Something that worked in real time to add gain to a weak input, but would quickly reduce gain in reaction to a strong input. That would be really good because then all the downstream stages would always have a predictably strong signal and never be driven into saturation or distortion. Ta-da! There's actually an IC that accomplishes these functions. It's the MAX9814 microphone amplifier with AGC, made by Analog Devices. Let's take a look at the block diagram. It has three amplifiers in series. First is a fixed 12 dB low noise gain block, then comes a 0 dB to 20 dB variable gain block, and that's where the AGC works, and finally another fixed block with three user selectable values. The IC also provides a low noise bias reference for the microphone element. Without getting into the messy details, let's just say this IC has a pretty sophisticated attack and release response to spikes in the input. There are user selectable parameters for the attack and release, so you can fine-tune the AGC response for the category of the audio input, like music versus speech, for example. But let's jump to the electrical characteristics table and see what's important to know here. First is the supply voltage. It looks like 3.3 volts is recommended. It'll work at 5 volts, but that's getting pretty close to the upper limit, and all the parameters are spec'd at 3.3 volts. So I'll plan on putting in a 3.3 volt regulator to feed it from the 12 volt bus in my transmitter. Supply current maxes out at 6 milliamps. So rough and tough, if I use a linear regulator to drop my 12 volts to 3.3 volts, it'll need to dissipate just over 50 milliwatts. And that's not a problem for something like the LDL1117. We can skip over the section on noise and gain for the moment. The next parameter of interest is the maximum output level. It's 0.7 volts RMS, or 2 volts peak to peak. There's a DC bias on the output of around 1.23 volts, and even though the output impedance is 50 ohms, we need to connect at least a 5K ohm load to the output and keep the load capacitance pretty low, no more than 200 picofarads. I think I can work with all these parameters. And to make using it even easier, Adafruit has taken this MAX9814 and packaged it on a tiny PCB complete with a condenser microphone and various other popcorn parts. All I need to do is provide a regulated power source. Nice! That saves me from fussing around with soldering that super tiny 3mm TDFN package. So that's what I'm going to go with. I built this transmitter with individual circuit board modules that closely match the elements in the block diagram. Now I did that deliberately as opposed to doing, let's say, just one or two large circuit boards so that future modifications would be a lot easier. And this little guy is a great example of that approach. This contains the microphone preamp and the low pass filter, so this is the only board I have to replace in order to make these modifications. I've updated the block diagram to show the MAX9814. I still need some low-pass filtering because I don't want to feed the balance modulator those frequency components above the bandwidth of single sideband, which is no more than about 3 kHz. I can't tell for certain what the dynamic range of the MAX9814 is, but it's definitely in the tens of kilohertz. Here's my updated microphone input circuit, shown side by side with the original. I've dropped the FET input amplifier. I don't need it anymore, but I am retaining the NE5532. There's 2 op amps in that SMT package, and my original circuit used one of them for about 26 dB of gain and used the second one for a unity gain Sallen key low-pass filter. In the updated version, I'll use both as low-pass filters to get a faster roll-off. These resistor and capacitor values set each filter to a 4.16 kHz cutoff frequency. More on that in a bit. I need an output here that maxes out at about 250 millivolts peak to stay compatible with the balance modulator circuit. But remember earlier when I said that the output of the MAX9814 is 1 volt peak and has a DC offset? I'm going to need to knock that down, and the easiest way to do that is with this resistor divider here, R1 and R2. Cap C1 will block the Max's DC offset and set a low frequency cutoff. R3 and R4 set a 6 volt DC bias for the op amp chain so I can use a single-sided power supply. And L1 is a 100 microhenry RF choke. I'm adding that to help block any stray RF that might try to enter the circuit. Let's take a look at some simulations. This first one just confirms that when I drive the input at worst case conditions, 1.25 volts DC offset with a 1 volt peak AC signal, I get the output that I desire. Just under 250 millivolts peak with no DC offset. I show here 500 Hz. Now that's a frequency well within the filter pass band. And this second simulation confirms that the filter network is working as expected. Note the 12 dB drop in the pass band. That's expected because of the resistor divider network and the op amp bias network impedance. The 3 dB roll-offs are occurring around 10 Hz and 3 kHz. Note that even though each stage has a 4.16 kHz cutoff, cascading 2 of them drops the 3 dB cutoff to about 3 kHz, and that's exactly what I want. Here's the performance of the original filter design versus the new one. I'm showing them plotted to the same scale, although I did have to subtract 52 dB off the original to account for the nominal difference in gain between the two circuits. There are 2 good observations to make here on the new circuit. The expected steeper roll-off on the high end, which will more aggressively filter out the unneeded higher frequencies. And there's a bit more now allowed to get through on the low end. Feedback that I got on the air from the original design was I needed more low frequency in my voice, so this should help a little. I want to have a baseline of what the MAX9814 sounds like before I put the low-pass filters after it. So all I've done here is just put it on the breadboard. I've got DC power coming in through here. It's off screen to my 2718 power supply, 3.3 volts. On the output, I've got a 20K pot just to provide appropriate load for it, and also lets me dial it down quite a bit so I have an appropriate signal level going through this cable into my laptop for data acquisition and being able to hear what it sounds like. And then lastly, of course, there's a 4.7 mic cap, I think it is here, just as a DC block, so I'm not feeding DC into that input. So let's give a listen to what it sounds like. Okay, and this is what the MAX9814 board sounds like without any low-pass filtering after it. And I'm speaking about 3 inches away from the microphone, and it sounds like my full range of low and high frequencies in my voice is coming through just fine. Now, one thing I'm a little concerned about is that this mic is very sensitive, so I'm going to get up and move across the room and keep talking. So right now I'm about 6 feet away and about 10 feet away, and now I'm at the far end of the room, probably about 20 feet away, and my voice is still coming through. So this is a concern that there's so much gain with this circuit, with the AGC control even in place, that it may pick up a lot of background noise. Okay, I've modified the breadboard circuit to add the NE5532. Here it is, right in the middle, along with all the resistors and capacitors that build up the low-pass filter network. The MAX9814 is still here, and I do have to maintain its 3.3 volt power supply on this wire, and then of course I need 12 volts on this wire here for the NE5532. It's all connected up to this very simple connection. Now here's that 20K trim pot still that'll lead through this connection to my laptop so I can record a sample of what the audio sounds like. Now I don't have L1 or C1. Those were on the input side, if you recall, on the schematic that I showed earlier. In particular, L1 was at 100 microhenry choke to help filter out any RF that might be there. I don't need that for this quick test, but nonetheless, the rest of the circuit is here. So let's give a listen to what it sounds like. And this is what the full circuit sounds like. You can tell that a lot of the high frequency components in my voice are now missing, which is exactly what the low pass filter is supposed to be doing. There might be a little bit of distortion coming through. I am using a pretty cheap input device here to get the audio into my laptop, but nonetheless I think I'm making the point pretty clear. And just like with the MAX9814 by itself, I still have this sensitivity issues, and backing away from the microphone. I started out about 3 inches away from it, and now I'm about 20 feet away from it, just like in that first audio sample. So I'm definitely going to have to be careful about background noise when I use this microphone. Now that I know that my circuit is working correctly, the next steps, of course, are to lay out a new circuit board, get it etched and get it populated and get it stuffed back into the rig and reassemble it. I've also got to put the MAX9814 into a suitable microphone. I happen to have one right here. These are the plastic shells for it. It's a $5 Hamfest special that I picked up last summer. So I'll show how I modify this to put that 9814 in there. And then, of course, try it all out. All of which will be the subjects for the next video. So as always, I hope you enjoyed this short little video on how I'm going to modify the audio section on my HF transmitter. And as always, I hope you're enjoying the material here on my channel. So until next time, bye for now.